Welcome to my channel Beneath to Zenith. Myself Obhijit. I'm going to create contents on various topics of higher mathematics and upload in this channel. This is going to be my first video in the YouTube platform, and I chose the topic group theory from abstract algebra to begin with. Before I get into the topic formally, I would like to brief how this concept was originated. Group theory is not a contemporary subject. Rather, it evolved over last 2.5 centuries. In fact, the evolution of group theory is directly related to the evolution of finding formulas of zeros of polynomials. To be explicit, if you consider group theory to be a grown-up tree, then the taproot goes back to the insolvability of a general quintic polynomial by radicals. Well, what does that mean? So what do we mean by solvability by radicals? Let us try to understand this first. So let's consider a quadratic equation ax square plus bx plus c equal to 0. For the historical relevance, let us consider a, b, c to be real numbers. And since it is a degree 2 polynomial, so this leading coefficient a is indeed non-zero. Then solution of such an equation is pretty well known by completing the square, etc. Then the solution looks like x equals minus b plus minus square root of b square minus 4ac all over 2a. So note that this expression involves a, b, c, which are coefficients of the original equation, and the elements 2, 4, which are elements of the base field Q, the field of rational numbers, using 4 basic arithmetic operations: addition, subtraction, multiplication, division, and extracting nth roots. So when solutions of a polynomial equation are expressible like this, we call that polynomial equation is solvable by radical. Okay? Alright. Well, this formula was known from ancient times. In fact, archaeological findings indicate that this formula was known as early as 4000 years from now. So it is a very old formula. Then what next? Obviously, next higher degree is the cubic equation. But solutions of cubic equation is not as straightforward as in the case of quadratic equation. Consequently, we had to wait quite some time, nearly 3500 years after this quadratic was solved, until Italian polymath Girolamo Cardano published the formulas of solutions of cubic and quartic equations in his book Ars Magna in the year 1545. The formulas of solutions of cubic was attributed to two other Italian mathematicians, Scipione del Ferro and Niccolo Fontana, who was more known to be Tartaglia. Well, the finding roots of a cubic equation itself is a very interesting rivalry story in the history of mathematics, to be specific in the history of Italian mathematics. And the formula of quartic equations was attributed to Ferrari, who was student of Cardano. So by the year 1545, we knew how to solve polynomial equations up to degree 4. Then what next? So next higher degree is quintic or degree 5 polynomials. Well, it wasn't immediate after cubic and quartics are solved. For about 225 years after Ars Magna was published, no progress was made for quintics or anything beyond. Then comes Joseph Louis Lagrange, one of the pioneers of modern day group theory. So in the year 1770, Lagrange published a landmark work on the theory of equations titled as Reflections on the Algebraic Solutions of Equations, written in French and consisting over 200 pages. So Lagrange's concern was the question of finding an algebraic formula for a general degree 5 polynomial equation. Well, what he observed that solution of cubic and quartic equations involved solving auxiliary equations of smaller degree than the original equations. These auxiliary equations are the so-called Lagrange resolvent equations, whose coefficients are rational functions of the original equations. Now, we will see how Lagrange used the notion of resolvent equations to solve a general cubic equation. Well, the germ of group theory is actually hidden in the construction of this so-called resolvent equation. Let us see this now. A general cubic polynomial equation is of the form ax cube plus bx square plus cx plus d equal to 0. Let us restrict ourselves with polynomials over real numbers. So a, b, c, d are coming from reals, and since we are assuming it to be cubic equation, so the leading coefficient is non-zero. Well, now this is 0 if and only if, just divide both sides by a so as to obtain x cube plus b by a x square plus c by a x plus d by a equal to 0. So this now becomes a monic polynomial. Now you apply the simple linear change of variable x equals y minus p by 3a, which is so called Sylow transformation. Due to this transformation, this polynomial, what happens? This will become a polynomial in y of degree 3, but its second highest degree, that is y squared term, will vanish. That is what we call depressed cubic. I mean, for any polynomial, if the second highest degree term is 0, we call it to be a depressed polynomial. So this will become depressed cubic. So it looks like y cube. Since y square term is absent, next term is py plus q equal to 0. Okay, now suppose alpha is a root of this equation, then alpha minus b upon 3a is a root of this original equation. That means as long as we are concerned about solvability by radicals, there is no problem. Why? Because this translating factor b upon 3a also obeys the law of radicals. Therefore, without loss of generality, we may and we will assume a general cubic equation of this form. So let's take this to be a constant polynomial later on. So let fx equals x cube plus px square px plus q, where p and q are real numbers. And let's say r1, r2, r3 are the roots of this polynomial f in some extension of real numbers. Let r1, r2 and r3 be the roots of f. Well, by that time Lagrange was interested in solutions of quintic. Vieta already established the relation between roots and coefficients of a polynomial. So by Vieta's formula, we have r1 plus r2 plus r3 equal to 0, second highest degree term is absent. Then taking 2 at a time, r1 r2 plus r2 r3 plus r3 r1, that is p, and product of the roots r1 r2 r3 equals minus of q, right? So let us denote this bunch of informations by 1. Then what Lagrange did, he considered omega to be, let omega be a primitive cube root of unity. Then omega cube equals to 1, certainly. And once you bring this 1 this side and factor, then since omega is a primitive cube root, omega is not equal to 1. So the other factor, that is 1 plus omega square equals to 0. And the value of omega comes from this solving this quadratic, that is minus 1 plus minus square root of b square minus 4ac, that is 1 minus 4, that is negative of 3 all over 2. Let's denote this by 2. Okay. Now what Lagrange did, he considered this 3 variable polynomial expressions, t of x1, x2, x3 equals x1 plus omega x2 plus omega square x3. Then what he did, he evaluated all permutations of r1, r2, r3 in this polynomial, and accordingly he recorded, he will find 6, because there are 3 factorial permutations, so he will get 6 values. So he gave 6 names to them. So let's say t1 is that, so r1 plus omega r2 plus omega square r3. t2 equals r1 plus omega square r2 plus omega r3. t3 equals r2 plus omega r1 plus omega square r3. t4 equals r2 plus omega square r1 plus omega r3. t5 equals r3 plus omega r1 plus omega square r2, and t6 equals r3 plus omega square r1 plus omega r2. Well, these 6 quantities, now we can apply 2 to express t3, t4, t5, t6 in terms of t1, t2 times some power of omega. For example, t3, you can see t3 can be equal to, so this 1 times r2, 1 means omega cube, so this becomes omega cube times r2. If you take omega common, then you will find r1 plus omega r3. So r1 plus omega r3 is t2. So this is basically omega times t2. Then again you express this to be omega cube r2 and this to be omega to the power 4 r3. Then what you find, omega square and omega r2, so omega square t1. Now here t5 equals by the same thing, it's like r1 plus omega r2, so this is your omega times t1, and this will become omega squared times t2. Okay, just one remark I would like to make here. So you can see, so we can have at most 6 different values here, t1, t2, t3 till t6. But while taking exponent cube 3 to all of them, I mean t1 cube, t2 cube, t3 cube, then they are taking at most two distinct values, namely t1 cube and t2 cube. That is actually at the heart of the construction of this resolvent equation. Okay. Anyways, while denoting this t1, t2, t6, we can also retrieve RIs in terms of TIs. How? If you add t1 and t2, what will you find? T1 plus t2 give us 2R1. So t1 plus t2 will give us 2R1 plus from these two you can take R2 common, then omega plus omega square. From here it is minus 1. So it is minus R2 minus R3. Now if you apply Vieta's relation, first relation, so minus R2 minus R3 means R1. So this becomes 3R1. So this implies R1 equals 1 by 3 T1 plus T2. Similarly, if you add T3 and T4, you will find 3 times R2. So we have R2 equals 1 by 3 T3 plus T4. So in terms of T1, T2, that is omega square T1 plus omega T2. Similarly, R3 equals 1 upon 3, then T5 plus T6, that is omega T1 plus omega square T2. So since we are actually interested in the roots of this f, I mean that R1, R2 and R3, and from this expression, isn't it enough to find the values of T1 and T2? Because once you know the value of T1 and T2 and you plug in here, you will find the roots. So it's now suffices to find the value of T1 and T2. So let me draw a box here. All right. Now observe one thing. What is the impact of permutation of R1, R2, R3 on TIs? So what if you permute RIs, then will TIs also get permute? Let's try to see this. So, so you are permuting on 3 element set. So either it is a transposition or it is 3 cycle. So let's take a transposition of this form without loss of gently. Let's take R1 and R2 are exchanging their positions. Then what is the impact of T1? Now you can see T1 means R1 and R2 are switched. So that means it is R2 plus omega R1. So can you spot it? R2 plus omega R1, that is T3. So T1 becomes T3 and also T3 becomes T1 due to this impact. So they are interchanging their position. Similarly, T2, so T2 is this. So if you interchange, it will become R2 plus omega square R1. So R2 plus omega square R1 is T4. So T2 will become T4 and vice versa, and T5 and T6 will interchange their position. If we apply any transposition 2 cycle on R1, R2, R3, that also act on this set as a permutation. Now what happens if we take a 3 cycle on this R1, R2 and R3? So let's say R1 is replaced by R2, R2 is replaced by R3 and R3 is replaced by R1. Let's try to understand what is the impact of this permutation on the TIs. So T1, after this permutation, T1 will become R2 plus omega R3. So R2 plus omega R3, that means T4. So T1 becomes T4. Now on T4 you apply this. So R2 will become R3 and this is omega square R2. So R3 plus omega square R2, that means T5. So T4 will become T5. And what about T5? R3 becomes R1. So R1 plus omega R2. So R1 plus omega R2, that means T1. So T5 becomes T1. Likewise, T2 expected to be T3, and T3 will become T6, and T5 will become T6 will become T2. That means even if you apply 3 cycle, then impact on this TIs again has some permutation. That means once you permute RIs, TIs are also get permuted. Okay, so can we say that we conclude that any symmetric polynomial in T1 to T6 is also symmetric in R1 to R3, is also symmetric in R1, R2 and R3. Well, when Lagrange was onto this solution of quintics, already Girard and Newton developed the theory of symmetric polynomials. So there they already established that any symmetric polynomial in n quantities is a function of the elementary symmetric polynomial of the n quantities, which means anything is symmetric in R1 and R1, R2 and R3 that can be expressible as elementary symmetric polynomial of R1, R2 and R3. I mean these 3 elementary symmetric polynomials. That means any symmetric polynomial in R1, R2, R3 can be expressible as a function of 0, P and Q, essentially P and Q. So we can say that any symmetric polynomial in T1 to T6 is also symmetric in this, and hence a polynomial of P and Q, right? Okay. Then what Lagrange did, he took this polynomial T minus T1 so on till T minus T6. So this is a polynomial for which T1 to T6 are the precise set of roots, right? Alright, so this is a degree 6 polynomial in T, and what are the coefficients of different powers of T? So coefficients are correct elementary symmetric polynomial of T1 to T6, but any symmetric polynomial in T1 to T6 is essentially a polynomial of P and Q, which means coefficients of this polynomial can be expressible in terms of P and Q as a function of P and Q. And with this information, T3 equals, everything is converted in terms of T1 and T2 with some power of omega. What we have after some rearrangement, it will become T minus T1, T minus omega T1, T minus omega square T1, and then T minus T2, T minus omega T2, T minus omega square T2. Now, what is the polynomial having roots T1, omega square T1, where omega is the primitive cube root of unity? So definitely this is the polynomial T cube minus T1 cube. So this is equal to T cube minus T1 cube, and this is equal to this part equals to t cube minus t2 cube. And if you simplify this, you will find t cube square minus t1 cube plus t2 cube times t cube plus t1 cube t2 cube. Well, again recall what we are really interested in. We are actually interested in the values of R1, R2 and R3. And in order to find R1, R2 and R3, it suffices to figure out the value of T1 and T2. That means once we know the value of T1 and T2, then we are done. But isn't it a quadratic equation, quadratic polynomial or quadratic polynomial whose roots are given by sorry, whose roots are given by T1 cube and T2 cube? That means if we can figure out the polynomial, this quadratic, we are done. Theoretically, what Lagrange already knew, that it is possible to express the coefficients in terms of p and q. So let us see how can we make it happen. Okay, so to simplify things, let us do one thing. We can take this factor inside so as to take a equals to, so let a equals to 1 upon 3 t1 and b equals 1 upon 3 t2. Then what happens? Okay, so then this r1 becomes a plus b, r2 becomes omega square a plus omega b, and r3 becomes omega a plus omega square b. But we know that r1, r2 and r3 are roots of this monic polynomial x cube plus bx plus q, which means fx is actually product of x minus r1, x minus r2, x minus r3. And upon plugging in these values here, and after routine calculation, you can see this polynomial is basically x cube minus 3abx minus a cube plus b cube. That's very simple calculation. You just need to use this too. That relation, something like that. Now you compare this expression with this original polynomial. Then what we have? So this basically gives us this minus 3ab is the coefficient of x, that is p here. That is 3ab equals minus p, and this a cube plus b cube is minus of q. Equals minus of q. So once you know a and b, it is very immediate, the value of t1 and t2. So what we are really interested, we have to find the value of t1 and t2. For this, enough to find this coefficient and this coefficient, because its roots are given by t1 cube and t2 cube, right? Okay, so what is the value of this coefficient t1 cube plus t2 cube from this information and this? So t1 cube plus t2 cube, so t1 is actually 3a, so it is 3 cube and a cube plus b cube. So this is basically minus 27q. And what about t1 t2? t1 t2 is 3a into 3b, that is 3 times 3ab, so it is minus 3p. and that would give us T1 cube T2 cube equals minus 27 of times P cube. Well, now we can plug in this and this value in this quadratic equation, quadratic in T cube. So thus RT takes this value, thus RT becomes T cube square minus this T1 cube plus T2 cube, that is minus 27 cube times T cube, then T1 cube T2 cube, that is minus 27 P cube, minus 27 P cube. Now we know how to solve quadratic equation, right? Well, this is what we call, this is what Lagrange called its resolvent for this cubic equation. Well, this is as a polynomial in T cube, it is a quadratic, so it is a smaller degree than the original equation, right? Original polynomial. So so its solutions are given by the formula of quadratic. So the polynomials that roots are T1 cube and T2 cube. So we are taking cube root so as to obtain T1 and T2 explicitly. So this is cube root of b square minus b plus minus b square plus 4ac. So minus b means 27 cube plus minus square root of b square. So 27 cube square minus 4ac. So plus 4 into 27 times p cube inside this cube root divided by 2. So plus minus, so if T1 is plus, then T2 is minus, and vice versa. Well, so now you find T1 and T2, so just plug in here in this expression and we can find the value of R1, R2 and R3, and we are done. So basically, to solve a cubic equation, we just need to solve a quadratic equation and then we are done. One remark I would like to make here, apparently when we take a cube root of a non-zero quantity, then it comes with 3 different values, right? So here T1 and T2 both have 3 different values. So don't make any mistake in understanding that both T1 and T2 has 3 choices, so altogether 9 possible values are there. This is not the case because of this relation. Because of this relation, T2 is uniquely determined by the value of T1. That means when you fix some value for T1, T2 is already determined. Okay. So since T1 can have 3 choices, so there are 3 possible values for R1. And once you fix something for R1, other 2 values are shared by R2 and R3. So there are essentially 3 roots for this polynomial up to multiplicities, obviously. Okay. All right. So this is the resolvent cubic for resolvent equation for a cubic equation. Resolvent equation turns out to be a quadratic equation, and similar thing happens for quartic as well. For a quartic equation, the resolvent equation turns out to be a cubic equation. Okay. All right. Thus Lagrange unified the existing methods of solving polynomial equations up to degree 4 in a hope that all higher degree equations also fit his method. Unfortunately, quintics did not fit his method. In fact, the resolvent equation of a quintic polynomial turned out to be of degree 6, which he did not know how to solve. This is essentially why Lagrange left the case of quintic inconclusive. No, Lagrange didn't make any mistake in his calculation of resolvent of quintic. In fact, it is not possible to obtain resolvent of a quintic polynomial of smaller degree than 5. After a few years, at the turn of 18th century, in the year 1799, Italian mathematician Paolo Ruffini made a valiant attempt to prove the insolvability of a quintic polynomials by radical. Again, after a few years, in the year 1824, Norwegian mathematician Abel, who gave a complete and clean proof of the fact that a general polynomial of degree greater or equals to 5 is not solvable by radicals. And this theorem is named after both Abel and Ruffini. Only after a few years of this, at around 1831-32, it was the genius French mathematician Galois who gave a complete characterization for a polynomial to be solvable by radicals. He developed a theory for this, named after him, called Galois theory. Surprisingly, Galois did everything before he turned into 21. In fact, in an unfortunate incident, Galois died at the age 20. And it was Galois who coined the term group in group theory. Perhaps the idea of Lagrange, of permutation of roots, inspired Galois to develop his theorem, which is why Lagrange's work is regarded as the cornerstone of the modern day group theory. For your self-exploration, some references related to history of group theory is added to the description box of this video. Thank you so much for watching this video. See you next time.